welcome to the Mathematicians Podcast, the podcast where we follow the fascinating stories behind the people that count in the history of mathematics. I'm your host, Benjamin Cornish, and today we are taking an oath to try to understand a lesser-known figure a bit better, Hippocrates of Chios. As you know, I used to have a friend who was a pirate. One day, he found himself stranded on a desert island with nothing but a broken compass. He told me he spent days trying to repair it, carefully aligning the tiny magnetized needle with bits of string and fragments of the casing he found washed ashore. He worked tirelessly under the blazing sun, using the stars at night to recalibrate his makeshift compass. Eventually, he succeeded, but when the needle pointed north, he looked out over the vast expanse of water and realised something unsettling. He had no boat to take him away. Now, you might think the story ends in despair, but it doesn't. With his repaired compass in hand, my friend felt a renewed sense of purpose. He began using it to map the island, marking its features, tracking the tides, and eventually piecing together enough knowledge to build a raft. When he finally set sail, his journey wasn't aimless. He had a direction. The compass wasn't just a tool, it became a symbol of his ability to think, adapt, and transform his predicaments into progress. Why am I telling you this? Because in many ways, the story of my friend mirrors the journey of one of ancient Greece's most intriguing mathematicians, Hippocrates of Chios. Like the sailor, Hippocrates faced his own version of shipwreck. Not a literal one, but a devastating professional setback that changed the course of his life. And like the sailor with his broken compass, Hippocrates found a tool to guide him forwards: geometry. Hippocrates didn't just survive his metaphorical shipwreck, he thrived, becoming one of the earliest pioneers to chart a course through the uncharted waters of mathematics. His story reminds us that setbacks, whether personal or professional, are often the starting point for our greatest achievements. With that, let's jump into the life and work of Hippocrates of Chios, a man who turned the wreckage of his career into the foundations of geometry. Now, don't confuse him with Hippocrates of Cos, the so-called father of medicine. The Hippocrates we're talking about today lived in the 5th century BCE, and is known for his ground-drawing work in geometry. If you've ever stumbled through a proof in a geometry class, you can thank, or maybe blame, Hippocrates for leaving his compass and straightedge lying on the floor. Hippocrates was another one of the early people to write a systematic book on geometry, after his teacher Oenopides, although both books are lost. He also made significant strides in understanding shapes, areas, and volumes. He's also credited with an early attempt to square the circle, a problem that fascinated and frustrated mathematicians for over 2 millennia. So buckle up as we journey back to ancient Greece to explore the life and work of this fascinating mathematician. To understand Hippocrates, we first need to understand the world he lived in. Hippocrates was active around 450 BCE, during what's often called the classical period of ancient Greece. Although technically still one of the pre-Socratics, but only by about 40 years. Mathematics in ancient Greece was primarily geometric. The Greeks inherited a wealth of practical mathematical knowledge from the Egyptians and Babylonians, but they took a different approach. Instead of focusing solely on solving practical problems, they sought to understand the why behind the solutions. They wanted proofs, logical deductions, and universal principles. The dominant mathematical figure before Hippocrates was Thales of Miletus, often considered the first true mathematician. Thales was one of the first to use deductive reasoning to prove geometric theorems, but Hippocrates built upon this basis, taking Greek mathematics into a new and more systematic territory. But Hippocrates of Chios was an unlikely mathematician. He wasn't born into a family of scholars, nor did he study at one of the great centres of learning. Instead, he came to mathematics somewhat accidentally. Hippocrates was born on the island of Chios, off the coast of modern-day Turkey. He wasn't initially a mathematician, but a merchant. As the story goes, he turned to mathematics after a rather unfortunate incident. While conducting his trading business, he was allegedly swindled out of a significant sum of money. Determined to seek justice, he travelled to Athens, a hub of intellectual activity. There, he became involved in philosophical and mathematical circles. And the rest, as they say, is history. It's important to note that Hippocrates didn't invent geometry. Far from it. He stood on the shoulders of earlier thinkers like Thales and the Pythagoreans. However, he was one of the first to write a geometry textbook, a monumental step forwards in the development of the discipline. In his book, The Elements, no relations to Euclid's more famous work on the same name, although some relation to his own teacher's book, also by the same name of The Elements. It's a real shame they didn't have robust trademark laws back then. In his book, Elements, he systemised geometric knowledge of the time. Though Hippocrates' Elements has been lost to history, fragments of his work survive through the writing of later mathematicians like Simplicius or Proclus. Hippocrates' most famous contribution to mathematics is his work on the quadrature of the lune. But what exactly is a lune, and why was this work so important? A lune, in geometry, is a crescent-shaped figure formed by two intersecting circles. Imagine taking two circular arcs, one smaller than the other, and overlapping them so they form a crescent. That's a lune. The problem Hippocrates tackled was to find a way to determine the area of the lune, using only straight edge and compass constructions. The significance of this lies in its connection to a much larger problem, squaring the circle. This ancient puzzle asked whether it was possible to construct with just a straight edge and compass a square with the same area as a given circle. Spoiler alert, the answer is no. It's impossible, a fact proven much later in the 19th century. But in Hippocrates' time, the problem was an open challenge. Hippocrates didn't solve the problem of squaring the circle, but he made progress by showing that it was possible to square certain lune shapes. He demonstrated that the area of a lune could be expressed in terms of the areas of triangles and other geometric shapes, which could then be squared. This was the first known example of calculating the area of a curvilinear figure using geometric methods. We should point out here that when we talk of squaring something, we mean constructing a square with the same area. Sadly, or happily in my opinion, in this world of pre-algebra mathematics, all problems needed to be posed in the form of geometry. Let's break down his method for squaring the lune step by step. Hippocrates started with a semicircle, then bisected the area to form a right-angled triangle with two radii. The hypotenuse of this right-angled triangle will become the diameter of a new semicircle. The lune created by the semicircle and the quarter circle will have the same area as the right-angled triangle. Try drawing it out first, then see if you can prove it yourself. For reference, this is something I would put up on my class whiteboard and invite my 16-year-olds to prove at the start of class. Spoiler, pause now if you want to have a go. Now, if we say the original semicircle has diameter 2, then the radius is 1, and thus the diameter of the new semicircle is root 2. This means that the areas have a ratio of 1 to 2. Therefore, the smaller semicircle has an equal area to the larger quarter circle. Given the segment of the overlap is subtracted from both these areas, the resulting lune and triangle will be equal. This result was astonishing because it showed that tools of straight edge and compass geometry could be extended to certain curved shapes. It was a glimmer of hope in the quest to square the circle, and a triumph of early mathematical abstraction. We may come back to this in 1,000 years when we discuss the lunes of Alhazen. Hippocrates also made early contributions to the problem of the duplication of the cube, another famous challenge in Greek mathematics. This problem asked whether it was possible to construct, using only a straight edge and compass, a cube with twice the volume of a given cube. Notice that this is a very geometric way of asking for the cube root of 2, by comparing the side lengths of both cubes. Hippocrates didn't solve the problem, but contributed by reducing it to finding two mean proportionals between a given length and its double. For example, if the original cube had side length a, he showed that doubling the volume required finding x and y such that the ratios a to x is equal to the ratio x to y, which is equal to the ratio y to 2a. This reformulation of the problem became the basis for later mathematical investigations. Hippocrates played an essential role in transitioning Greek mathematics from empirical methods to deductive reasoning. The Greeks inherited practical geometric techniques from the Egyptians and Babylonians, but Hippocrates sought to provide rigorous proofs rather than relying on measurement or experimentation. His work exemplifies the Greek focus on logic and reasoning in mathematics. One of my favourite classroom tricks is to ask my students to draw a perfect square with area of 10. I give them a few minutes with their square paper. Obviously 9 squares would be easy, but 10 feels like it should be possible as well. When they give up, I draw a very deliberately wonky square on my board, possibly not even connecting the corners together, and inside I write area equals 10. The joke here is that for something to be accurate, we have to state it, then use that value for later work, rather than have things empirically drawn correctly. Hippocrates' work on the lunes may seem like a mathematical curiosity, but its significance cannot be overstated. First, it represents one of the earliest uses of deductive reasoning in mathematics, a hallmark of Greek geometry. His approach set the stage for later mathematicians like Euclid, Archimedes, and Apollonius, who would refine and expand upon these methods. Second, Hippocrates' work introduced the idea of reducing complex problems to simpler ones. Instead of tackling the impossibility of squaring the circle directly, he focused on specific cases, like the lune, that could be solved. This problem-solving strategy remains a constant of mathematical thinking today. Finally, Hippocrates' Elements was an important precursor to Euclid's Elements, the most influential mathematics textbook of all time. Though Hippocrates' work is lost, it's clear that he played a crucial role in organising and systemizing geometric knowledge, making it accessible to future generations. Hippocrates of Chios may not be the most famous mathematician in history, but his contributions laid critical groundwork for the development of geometry. His work on the quadrature of the lune demonstrated the power of logical deduction and the potential of geometry to tackle complex problems, and his efforts to systematize mathematical knowledge inspired the tradition of rigorous scholarship that endures to this day. So, the next time you're teaching or taking a geometry class or puzzling over a tricky proof, take a moment to appreciate Hippocrates of Chios. His ideas, though ancient, continue to shape the way we think about mathematics. Thank you for joining me on this merry-go-round of historical stories. I hope your understanding feels squared off. If you enjoyed today's episode, don't forget to subscribe to the Mathematicians Podcast and share it with your fellow maths lovers. Next time, we will be swapping the Ocrates for an Eas, so you'd be an Eas to miss Hippias of Elis, next week on the Mathematicians Podcast. Until then, goodbye. The music today is Danse Macabre Finale by Kevin MacLeod. You can find more information in the show notes.